any shareized product over, Uber pool. Oh, okay. This is actually the largest group I've ever seen. I asked this to my undergrads at the so this is great. So I don't even need to do a lot of setup on what I'm talking about. Obviously, this is an ITS seminar. Everybody is very, very sensitive to this. Yeah, okay. So the motivation is solving congestion problem, right? It's kind of a lot of people in this room probably spend a lot of time on this fund. There are a lot of bad negative externality in terms of congestion. People waste time. It's not actually good for the society, for the welfare. And the focus or proposition I'm going to focus on is, people have been thinking about using share rights, in the past decades, thinking about putting more people into the same vehicle, right? So in this case, you're able to reduce the flows and then reduce the congestion. I'm particular because of my own experience. I'm going to particularly tackle this problem from the perspective of ride-sharing services, in particular Uber, Lyft, and Didi, have been gaining traction over the past decade. I guess everybody knows Uber, Lyft, but probably what you don't know or not so familiar with is that both company actually has a close tie with share rides product, especially Lyft. Actually, so if you look at the history of Lyft, so they founded out of early startup called Zimride. So this is actually a bunch of Cornell students, their co-founder, trying to set up a carpool platform for Cornell students from Ithaca to commute to New York City, right? So that's actually how Lyft started. Uber, interestingly, if you search the previous CEO, Travis Kalanick, on YouTube, there's a quite inspiring TED Talk that he was talking about, the vision of putting more people in the same vehicle and this idea of infinite chain, right? So you have this vehicle that pick up, drop off, that just never stop, right? So thinking about these type of problems, actually, when both platforms started, they have a lot of vision. In fact, the two platforms are competing on the launch day. So the launch day of Uber Pool and Lyft Line actually only differ by 1 day. So Uber is 1 day ahead of Lyft. But there's a lot of fierce competition on actually who launched the first carpool product, and they kind of brag about it. So I vividly remember this because around that time, I was, I don't have a lot of money. I make a pool of grad students who actually use these services. Before IPO, they have a lot of investment, right? So actually, I remember when I was in my grad school, you can actually get very cheap Uber Pool rides and Lyft Line, right? Up to a point, actually, these services actually comprise of 30 or 40% of their regular trips. But during the pandemic, for obvious reasons that initially because of healthcare reasons, both platforms decided to shut down the service. That's why you see there's a gap here. There's basically no share rights portion. So here, what I'm plotting here is I'm plotting this light blue is the fraction of share rights requests, and the dark blue is the amount of share rights requests that are actually pulled together with something, right? So probably you have experienced that you call it Uber Pool Lyft Line, and because of the uncertainty about demand, you actually ends up riding solo, right? So these are the fraction of trips that are actually flight matched. And then after the pandemic ends, those platforms decided to relaunch the product, and Uber actually rebranded for a different name, called Uber X Share. Lyft relaunched it, and there's actually a very unfortunate news last year. Lyft decided because of financial reasons. They had a new CEO came in and they have some financial difficulties. They actually decided to completely shut it down. So Lyft has no carpool products anymore. Open up Lyft, which is a sad news because kind of they started with all these great idea about carpool. Right? So this is really kind of the backdrop to focus. Okay. The next news. Okay, so this is around the time. Let me see this news. Yeah, 2017. So this is around the time when I joined Uber. So I actually vividly remember that they're trying to, at the peak of launching a new carpool product called Express Pool, which is, I'm not sure how many you've heard about this, but it's the cheapest ride-sharing product. They ask you to not only pool with somebody, but also wait a little bit and walk to certain pickup points, right? So they're able to improve the cost efficiency. But what's the reality is that to gain the certain match rates, they actually heavily subsidized, right? So they actually burn cash. Remember when I live in Mission Bay, San Francisco, right? You call Uber Express Pool to SFO, sometimes it's only $2, right? So it just does not make sense. Sometimes the price point are too low just to gain popularity. Let me just give you some quotes on what actually happens, right? So one rationale people were thinking about that to justify why they're burning too many caches, if you burn enough upfront and get those economy of scales, which actually I'm going to talk about, and then you have more demand, right? And the idea is that, if you have more demand, then your match rate is going to be high. So eventually your cost goes down so that you can be self-sustained, right? So this is kind of one hope that why burning cash at the beginning can help. But, the reality is that they haven't seen this. So they just keep throwing cash into incinerator, and then it's not able to actually see whether it's able to make it either a popular product or at the same time it's also sustainable in terms of profit. Okay. Yeah, and then when they cut the heavy discount, they see the variation of tax, right? So this is basically the key tension I want to focus on in this talk, right? So if you're thinking about share rides, people working in transportation knows that there are a lot of complexity, right? Thinking about routings, matchings, how you efficiently route your vehicle, pickup, drop-off sequence. But in this talk, I'm just going to focus on a very simple tension around pricing. Okay, I'm going to talk about why pricing is not that simple, and then what is the difficulty challenges around pricing these products. And in particular, I'm going to talk about these two trade-offs, right? So I kind of mentioned in this news that prices has to be low enough to be attractive enough so that people are willing to share. You have enough demand. But on the other hand, if you charge your price too low, you have risk, right? Risk in terms of they offer you a discount, but you actually ends up riding solo. So the platform actually lose money in these rides, right? So oftentimes the platform trying to set prices to strike a balance between these two goals, but they're kind of either too high or too low, right? So they're not able to actually find a delicate balance. This is the difficult. I'm going to focus on. Okay. Any question before I move on the setup? Good. Okay. So let's briefly talk about literature. It's not a new idea. So there's a lot of work thinking about share rides. In particular, there are tons of work on routings, matching, right? And in particular, I will highlight, the second one, which is talking about a high capacity vehicle setting, where they look at the New York taxi data set, trying to see how many vehicle you actually need to, with efficient carpooling, you're able to serve all the taxi demand, right? And then this famous Senti paper talking about carpooling matching and matching as well, right? So there's a lot of focus on how to match and route. The second stream of literature is focused on flexibility, right? So thinking about adding a little bit of waiting time, maybe thinking about walking or detours, trying to think about how these is going to impact the efficiency of these share rides product, how to thinking about the service level, how to design this product in terms of amount of inconvenience versus the efficiency you can gain. And then there's pricing, which is actually more relevant to this particular talk. But if you look at most of the pricing literature prior to this work, mostly they focus on, I would say, overall equilibrium behaviors, right? So thinking about if you set some kind of market price and these are the demand and the supply, and then as I will go deeper into the model I'm going to look at, we focus a lot on the detail dynamics, which is actually the key point of this work. But the prior work mostly focused on kind of more general equilibrium steady state behaviors. Okay. All right. So what's the point of this talk? What's the contribution, right? So the contribution is we're going to first trying to explain things. We're trying to say, oh, why this problem is hard. We're trying to explain why pricing share rights is not as easy as price some other products. For example, the regular solar rights. In particular, the way I'm going to do this is I'm going to analyze status quo pricing policy that have been used very popular in platforms, and then trying to show why these straightforward pricing policy can fail. Okay, and then hopefully convey some insights around that point. And then after explaining this, I want to propose a new pricing policy, or I would say more like a pricing strategy, which we call it's an adaptive pricing strategy, and which is actually it's adaptive to the matching outcome. We can call this a match-based pricing. We're going to illustrate, but when we get to the slide, things will be clear. But this is the agenda of this talk. Okay. Good. So let's talk about what problem we're going to study using a very, very simple model. I'm going to call this model the simplest share rights model. Right? Thinking about a very simple setting where everybody go from the same origin to the same destination. Okay, thinking about you're getting off a flight, you're arriving at the airport terminal. Everybody want to go from the Oakland airport to Davis. Okay, so and then the attention we're going to capture is the arrival is stochastic. So the arrival, you don't have the full information about the future arrival. So the arrival sequence is kind of a stochastic process. Thinking about a Poisson process, you only understand kind of the process, but not the exact sequence. Okay. And we're gonna assume that there are sufficient supply to service demand. So we're not worried about routing at the moment. So thinking about cars kind of magically appears at the places they're required, right? So the tension we're gonna focus for now is on the demand side. So you always have enough supply, okay? And let's look at a case with you only have a capacity of 2. Okay, but it can be generalized to other cases. But for simplicity, let's look at every vehicle can only hold up to 2 passengers. Okay. So we also assume that thinking about the share rights, like everybody arrived at this airport is opting to share with somebody. So there is no separate solo products, which is oftentimes the case. You can choose to ride solo versus ride shared. In this simple model, just think about everybody is willing to share with each other. Okay, we have some in progress that are looking at the extension, but for simplicity, let's assume that. So what's the division variable? So the division variable, because matching is actually straightforward in this case, right? People randomly arrive over time. So what do? You wait until if there's 2 passengers, you match them, right? And then so basically, there's no fancy thing you can do because they all go from the same origin to destination. So if there are 2 passengers on hand, you just match them and you dispatch a car, right? So the only issue here I'm going to focus on is the pricing. Just thinking about how much you can charge for this product, okay? And there is a price you're going to charge, and there is a cost of the platform that is, thinking about a driving cost from this airport to Davis. Right, and then the way we're going to model conversion is that riders are sensitive to price, and then thinking about a very simple econ model where rider has a valuation that is drawn from a uniform distribution from 0 to 1. So if the valuation is higher than P, then the rider is going to convert. If the valuation is lower than P, then the rider is not going to convert. Right, so the utility of this rider is the valuation minus the price. So if I set my price as P, the conversion probability when a rider see this price point P, it will be 1 minus P.
Is that unique to the individual, or is that for the whole population?
Yeah, it's a static price. Everybody arrives, see the same price P, and then have a conversion probability of 1 minus P.
Yeah.
Okay, very, very simple model. So this is basically what happened. Everybody's going to see the same price point, 7.68, and then there is a lambda probability that this person is going to request, and then there's 1 minus lambda probability that the person decided to go to other options. Okay. We also have this patience. Okay. Thinking about this patience as every rider is willing to, for example, wait for on average 5 minutes to wait for another passengers to pull together, right? Thinking about the Uber pool product you guys have been using, right? Sometimes they have a batching window. They will say, they have a spinning screen. They will say, oh, they're trying hard to match with somebody. But if they don't match with somebody, they will send you a call, right? So thinking about this patience as this 5 minutes waiting window that a rider is willing to wait to match with somebody, okay? So we model this patience as a rate theta. So thinking about this as there's a Poisson rate of theta, or every rider has a patience that is drawn from an exponential distribution with the rate theta, right? And then this is basically what the model is. So here is basically the dynamics, right? So the riders will arrive and then make a request at rate lambda. This lambda is determined by your price point. And the platform dispatches when there's another rider arrive and there are 2 requests waiting, they will just dispatch a single vehicle, right? And the other case is if the patience of the first rider elapses, so the platform has to dispatch a single vehicle. Okay, so this is the dynamics. Okay, so it turns out that you can model this dynamics with this very, very simple 2-state continuous time Markov chain. Anybody here has never heard about Markov chain in this audience? Okay, you all have some knowledge about this. Okay, good. So basically the idea is the state variable in this Markov chain will be 0 and 1. So these are the number of riders waiting to be dispatched, right? So if you're at state 0, you're going to go to state 1 with this lambda rate, which is the arrival rate of another new riders. And then at state 1, you're going to go back to 0 with the rate of lambda plus theta. So why lambda plus theta? Let me walk through this. So this lambda here is the arrival of another new riders, right? So if there's another new riders arrive, then they got dispatched immediately together. So then they got cleared, right? So then there's only 0 people in the system. Or this waiting riders renege with the rate theta. It runs out of patience. So you all go back to 0. Okay, so this is the dynamics of this stochastic system is if you track the number of riders that are waiting to be dispatched, it is a simple continuous time function. Okay, and then the decision variable here is the lambda. We're going to the platform is going to use price to influence this lambda, right? So thinking about pricing decision as thinking about, I'm going to control the amount of demand rates coming into the system. I'm going to let more rider requests or make fewer rider requests. This is basically the problem. Any question before I move on for this simple model? Good? Yes. Okay. So let's talk about using this model, how we're going to come up with the optimal pricing policy, right? So what the platform is trying to maximize, assuming that the platform is not altruistic, is for profit, it is going to maximize the profit, which is lambda, that's the throughput rate, times the price, which is 1 minus lambda, right? Remember, if I set P, then my conversion is 1 minus P. So the other way to say this is if I set a conversion to be lambda, the corresponding price is 1 minus lambda, right? So that's the price I collect minus the expected cost. Okay, so the cost is the tricky part of this model because it's not certain, right? In a sense that sometimes you actually ride alone. So the cost is actually exactly C because they actually paid one driver to drive you from origin to destination. But also sometimes you're going to get a match, right? So there are, this match rate is going to bake into the calculation of this cost. Okay, so in fact, you can actually, you can solve this cost. So here I give a formula here, and then really the way to get this formula is I'm going to go back to the previous this Markov chain is you can actually for the simple Markov chain you can actually get a steady state distribution of the system being in 0 and 1. So given a particular rate lambda, you can actually work out what's the match rate in the sense that what's the percentage of rights that are matched, right? And then this basically goes to this formula. I'm not going to go over the derivation, but you can actually solve the steady state distribution of this two-state Markov chain in closed form. You can actually get this formula. Okay, so this makes sense because as lambda goes up, your cost decrease, and then it approaches asymptotically to C over lambda, right? Which is the best cost you can get, because if you always share with somebody, then your cost is C over lambda, and then if your lambda is 0, then your cost is C. So you have this diminishing return in terms of your cost. Is it making sense? Everything here? Right. Good. Okay. So this is nice because now I can put this C bar lambda, this expected cost, into the profit function, right? I can actually solve this optimization problem. Okay. But if you think about in practice, when I say in practice, I'm not talking about this particular origin destination, right? I'm talking about all kinds of multiple origin destinations. There are people going from A to B, C to D, right? It is actually really hard to figure out what this C bar lambda is, right? In here, I can reason the C bar lambda with this simple Markov chain model with this assumption. But if you ask people in these platforms, how are you going to evaluate the cost under a particular pricing plan? It's just a super complex, it's a black box, right? So why? Because it's all interconnected. There's a network effect. So whatever price you charge on particular origin destination is going to have impact on other origin destination if they have relation, right? So this is actually a very complicated form if there even exists a closed form, right? So what people do in practice is actually not solve this problem in this type of way. What they do is they're going to do something called a practical or a iterative pricing heuristic. Okay, so let me walk you through this iterative procedure that is widely popular, very popular in platforms. So the idea is you're gonna start with some initial pricing plan. Okay, you don't know what the optimal pricing plan is. Let's just start with some initial pricing plan for each origin destination, and you publish this pricing plan. You let the system run for a month, right? You let the system run a month, and then you could compute the average cost for this origin destination, right? You can run this you can publish the pricing plan. You can also just run a simulation. You have a simulator, and then these are the rival, and then you get the cost of each origin destination, right? And then you use this cost, and then you assume that this cost is actually not a function of your price plan, and then solve the simple price optimization problem, which is simply, lambda, which is the conversion, times the price minus the cost, which is 1 minus lambda minus C, right? So the only difference here is the C. Before the C is actually a function of lambda. Now, when I'm doing this heuristic, I'm assuming that my cost is fixed. It's not going to change by price, right? So what I'm going to do is I'm going to repeat this procedure multiple times until it converges, right? So I have a simulator, or I just implement this in real setting. I have an initial price plan. I look at what the underlying cost corresponding to this price plan. I calculate the average cost. I re-optimize the price, and I run the system for another month, and then I do it again. Any question before is it confusing or good? Yes, yeah.
So you're doing this operation for every person that is requesting the service in pool mode.
Yes.
And this is like in the computers at Uber centralized, and you're computing this iteratively.
Right. So, okay. So say you just start with some price plan, right? This will be, you can do a very simple price plan. Let's say it's going to be a fraction of time and distance, right? And then you can implement this in practice, right? And then you can see what's the actual match rate in practice. Maybe this particular rights going from Davis to the Oakland airport, in all the historical data in this 1 month span, 20% of them got matched, 80% of them is not matched. Among these 20% of matches, these are the amount of overlap, right? So you could actually look at what actually happens under this pricing plan to say, oh, this is our highly matchable origin destination. These are not that matchable origin destination. Just look at what actually happens. Okay, so then with that, you can actually have some understanding about how these origin destinations are more efficient than the other. Yes, questions?
So do you also assume that after two riders or potential rides are matched, they're not canceled right after? Is there, if people change their mind right after, is that something that's also assumed?
Yeah, so in practice, there are cancellation, but let's just, don't worry about that for now. Just thinking about everybody, or you just look at all the accepted, or maybe cancellation could be part of the calculation as well, right? So maybe you look at amounts of data, there is 100 requests from this origin to this destination, 10 of them canceled, and then they're solo, right? And then maybe 30 of them got matched with somebody with this amount of overlap, and then the rest. So you can actually averaging these out, saying that this is what's the on average efficiency of this origin destination, right? And then the intuition is that if it's more efficient in the sense that if it's highly matchable, you want to reduce your price because, but the tricky thing is that your price is going to change your cost, right? So we're not going to explicitly model this, but we're just going to publish some price plan, run this for a month, see what happens, update the cost, doing some regression, resolve the price, and then just do this multiple times. Okay, so it's a heuristic people use a lot, and it's make a lot of sense. Right?
So I guess if it takes a month to do iteration, and what do you know about the convergence of is it even practical to do something?
Right. So what typically there's a digital twin, right? So oftentimes people will run this with simulation.
Yeah.
That will be faster. Another reason people do this in practice is trying to capture non-stationary. Is if I go back to your point that if it takes a month to collect and sometimes they're just seasonal effects, so they're trying to use this also to capture non-stationary. That maybe I want a different price plan because demand pattern is different.
Yeah.
Over. But typically people will have a digital twin just to speed up.
Yeah.
Yeah.
Okay.
If it's an optimization problem and you're looking to increase profit, how do you design it that it doesn't go higher than always going solo? And then people will be like, it got more expensive because I tried pool. Even if you're going alone, it would always, in my experience, be cheaper than not clicking on pool. And on the other hand, there's a driver component.
Yeah.
How did that, because I'm interested in see how did you factor in the people getting less, paid much less with this service?
Right. So so typically people will have some floor to solve. Here I'm actually doing a very simple price optimization, but you could have optimizing prices for two products. It's like there's a solo products and there's a shared product, and then you put a constraint saying that within this optimization, you cannot allow the pool price to be higher than solo product. Right. So hopefully this is natural without this constraint. Even our solution will have this, but for whatever reason, sometimes there are data quality and then there might be weird, but there will be oftentimes guardrail to prevent things from that happen. Your comments of getting higher and higher, actually that's a perfect segue. I'm going to talk about that by analyzing this. Let's defer this to the next slide. Your comments about drivers, yes. So usually the way it works is things are changing now, but usually the way it works is driver are paid by the distance, the amount of driving, right? So it's usually independent of you have two passengers on a vehicle or one passenger on a vehicle. So oftentimes, one argument you can make on why sometimes, obviously there are downside of picking up share rides because you have to pick up additional passengers. But the other argument saying that driver might like this is because it can increase their utilization, right? Because you actually constantly picking up drop off people. So your idle time sometimes can be smaller. So, but it's up to discussion. So it's less clear on which way it will go. Yeah. Just because of the way that the driver pay is calculated. Yeah. It's making sense. Yeah.
In the historical data, how do you, let's say, compute the efficiency of matching or the average price when you're looking at isolated events when there's a surge in demand? So let's say there's an event going nearby, and you know that in those cases, potentially the efficiency would not conform to what had happened in the past, but rather is an independent metric based on the event that's happening.
Yeah, so these are all averaging out these edge cases, right? So in particular for the surge example we're talking about, so that actually has to do a lot with supply. in a sense that why they surge is because they don't have a car available. This way of thinking, really trying to separate supply out, thinking about it's only about matchability of demand. But you're right. So in practice, it's never that clean. There are supply scarcity, there are events, but I just want to give a overall big idea that this is a reasonable way to do it. Is that if you don't understand, because figure out the cost is actually the punchline. The punchline of the slide is figure out the cost is actually difficulty of pricing share rights product, because the cost is uncertain. You don't know who you're going to match to, right? For solo products, you always know this is the time, this is the distance. There might be some uncertainty in terms of travel time or traffic, but a big uncertainty in share rights is you don't even know who you're going to match to. You don't know that amount of overlap. So that's actually the punchline of why pricing this product can be tricky, is you don't even know the cost, right? So I want to just throw out an idea that are very reasonable, that if you don't know the cost, let's just run some experiments, understand the cost, and update it. Yeah. Okay, so it turns out that you can actually analyzing this dynamics. Okay, because what I described here is a iterative procedure, right? So you can actually analyze where this thing converges to. Okay, and because the way it's set up is actually have closed form that we can analyze. What's interesting about this is, so the idea is if you start with, let me just show you visually what is happening. Right? So you start at, I need to point over there. Suppose you start so this blue point is the highest profit point. That's the best optimal price point, right? Suppose you don't know that's the optimal price, you start as this gray point, right? And then you see what the cost is, and that's your next point, right? And then hopefully this thing is going to converge to something. Okay, so this is so it turns out that you could, analyzing this, that you can show that this is going to converge to, depending on where you start from, to 3 values. Lambda upper bar, lambda lower bar, and 0. Okay? And what's nice about this is that regardless of converge to either of these 3 values, you can show it is always overpricing. So it is always, whatever it converges to is going to always be higher than the optimal static price if you know exactly what the cost will be. Okay, so this is the first punchline, is that this heuristic is actually what leads to overprices. Okay, so what's the intuition of this? The intuition is also very clear, because when you're thinking about you're updating your price based on the current cost, you did not take into consideration that if I lower the price, I'm going to get the product being more cost efficient, right? So you don't take into account the positive externality of lowering the price. You just assuming the cost is fixed, so you update your price, and this will naturally lead to overprices. Okay, so if you want to go to let me just give you one more example. Yeah, this is a more natural case where your cost is relatively low, and then in this case, no matter where you start, you can always converge to this lambda bar, upper bar, which is lower than the optimal lambda star. In some cases, when cost is actually relatively high, you actually will have this weird situation, which we call call it timid entry. So the idea is, okay, so here I'm plotting the starting point, right? So if your starting point is actually too low, let's say if your starting point, the first price point you pick is, too high. The first price point is even higher than 1 minus lambda lower bar, you will actually gradually price yourself out of the market. So this goes back to your point, is that if you enter the market with a relatively higher price, iteration after iteration, you kill yourself, basically. There's no demand at all. So you're basically entering this weird dynamics, is that the price reaches upper bound and then there's nobody using it. Okay, so the manager insights here is that if you want to use this type of iterative methods, you probably want to start with lower prices. Just take some risk at the beginning, and then hopefully it will convert to something at least reasonable, right? So if you start with something high, you will even kick yourself out of the market. Okay, so this is another insight we have from analyzing this dynamics. Any question before we talk about before we move on? Good.
Well, it might be basic, but I'll do it.
Yeah.
So you said you have millions of rides at the same time in the whole world.
Yeah.
So you took this month of data and said this is the probability for this trips at
Yeah.
this cost, and then use that data to establish this fixed cost.
Right.
And then how did the feedback, like the AML
Yeah.
that you're gonna see?
Right. So you have the cost. You
update.
say this is the cost. That's
In
just
real
assuming it's a
time.
constant. Right. Then you just think of if I know this is the constant cost, I just price on my demand curve to maximizing my profit. Right. My profit will be the price minus the cost times the demand. So you could just solve that simple price optimization problem, assuming that you know the cost, right? So then, with this new price, you run for another month, your cost will change, right? Because it's under a different price point, so that the demand rate is different, right? The whole thing about the cost is because it depends on the demand rate. So then you're gonna do another cost. So what this is trying to say is that your initial price probably should not be too high. If you start with all these millions of origin destination with relatively high price, if you run this multiple rounds, it's going to keep higher and higher the price. And then eventually you basically drive yourself out of the market. So you want to enter the market with a relatively lower price so that it will stabilize and converge to something better. That will still be higher than the optimal thing, but it will at least not be zero.
Because you knew this, they let you implement. Even though the news said you were losing money at the beginning, you knew it was going to be.
No, this is
recovered.
in hindsight. This is analyzing the existing policy. This is what the platform we're doing over the years. This is me coming from I'm coming as a researcher trying to analyze it. This is not my work. Yeah.
And so you observed that from the numeric analytical solution, and you're not doing this like numerically, right? It's not like a gradient thing. You see this from the.
Yeah, so you can prove this analytically.
Oh, okay.
You can actually prove the whole thing. The whole thing I just described. You can prove by.
So then what's the like too high price?
Yeah, so there is a threshold. I think you train. So there is a closed form formula for this lambda bar, which is complicated. It has a square root of things. But for this simple system, you can analyze this completely. You know, if you start with this price plan, will be the point.
So you didn't do this operation for every trip iteratively, but you did this kind of, or whoever did it monthly to update the base costs every month and then run the variables.
Yeah, you could do this way. You could run this in simulation. I would say in simulation probably is more effective.
I was thinking of like the computer power of the machines. I know there's a limit to that.
Yeah, but you can simulate. Let's say you don't need to compute on what the price point is, but you can always simulate what happens with this. You can say, you can backtest your data, right? Let's use the past amounts of data with this particular price point. I have some understanding about demand, and this is what the match is going to happen under some matching algorithm.
So when you use it, it's going to go to one of these solutions that we're already simulating.
Yeah, so you're going to simulate this multiple run. Let's say if you want to use this approach, what you're going to do is you're going to simulate this multiple runs, and then you're going to converge to something. And then you're going to publish this in real life, right? You use the simulation outcome to guide your actual price points, and then you're going to publish this. Making sense? Yeah, okay. Okay, so let me see. Right, so this is just trying to justify there's this Atlantic article talking about Uber Pool is zombie in the sense that it's kind of there, but it's no one is using because of kind of price points is too high, right? So I'm trying to give some idea on if you're not using the right pricing strategy, sometimes weird outcome can happen because of this dynamics. Let me talk about kind of the important thing here. I guess the solution we propose. So the solution proposed is a different pricing strategy called match-based pricing. The idea is actually simple. So if you think about all these, the traditional way of pricing these products is something called upfront pricing. Right? Upfront pricing is actually how ride-sharing services are gaining traction. Is prior to ride-sharing services, the amount of you pay is depending on this meter. Right? So sometimes you actually don't have a guarantee about. So that's why these platforms use this upfront pricing, which is this static pricing. They compute this cost and they come up with a static price. But what I'm going to argue is that this is actually not a good idea. because of it's hard to compute and also it has this weird dynamics. And what I'm going to propose instead is something called this alternative state-dependent pricing policy. Okay, so what does this mean is that really the amount that you pay is going to depend on the matching outcome. So I'm going to draw your attention on the second thought here is if you go to the current UberX share product, what happened is they actually offer a price menu, right? So the price menu says that if you are the first rider, if I'm not certain that you're going to match with somebody, you're going to pay a relatively high price, right? And then this high price is subject to discount if you actually end up match with somebody. So for example, I'm going to show you two prices. The first one is $10. The second one is $8, right? You pay $10 if you end up riding solo. But if you end up match with somebody, you're going to pay the discount price. So there's a two-tier pricing. Okay, so that's the idea. The third graph is something also quite interesting. Is if you're opening up the app, you're calling a ride from a particular origin to destination. Because the system actually can track the existing request. So if it finds that there is a nearby matchable request, it will prompt with this discount, right? It will say, do you want to join the share rides with this additional discount, right? So this is the second example I'm talking about match-based prices that you can actually use the matching outcome to guide your pricing, right? So you don't have to actually figure out all these uncertainty, calculate expected cost, and then come up with a static price. What you could do is actually, let's just see what happens, right? It's not certain, but you can actually, based on what you realize that the matching outcome is, you can adjust your price, yes.
Can you switch back between different states? So let's say you do accept the shared ride, but the person who's gonna come in next decides to not share the ride with you because you're taking too long or there's traffic. Can you revert back between different states?
Yeah, so in this model, I'm going to talk about there's no disincentive compatible issue, but you're absolutely correct. There's an issue on if I'm the first rider, you promised me with this amount of detour, and then now you add another rider, it might not be incentive compatible for me to say yes. But in this case, I'm assuming that there is an agreeable detour amount. People, you can add passenger within this limit, but you're absolutely right. So that could be an issue. Another question? No? Okay. So the idea is the rider gets a discount if the rider ends up being shared, right? So you will have, instead of having the single price, now you have the price menu. You have a solo price, which is the initial price you offer. And if you share with somebody, then you're going to be updated to a lower price. Okay. So the way to think about this is there's two variables you're going to optimize. One is this P prime 0, which is the price if the ride ends up being solo, and P1, which is the price if the ride ends up being shared. Okay. And I'm just going to skip the math. And then the next component of this pricing strategy is that if you or a rider actually come in when you arrive, the system knows that there's already somebody that is matchable. You will only see the second price. Okay, so that's a mechanism the system actually can lure riders to request because they know that it's already a good match. So they can reduce the price, so they can incentivize people to move. Okay, so this is the pricing policy I'm going to analyze. Okay. Right, so this is basically the prediction. So the nice thing about this is that you can actually use the same model I was talking about, the two-state Markov chain, to analyzing this problem. The only difference now is instead of before, I'm not sure you remember, I have a single lambda going from 0 to 1, and the same lambda go from 1 to 0, which is lambda plus 0. Now the only difference is you have two lambda. You have to figure out what is the price you code when there's nobody waiting, that is the lambda 0, and what's the price you can code when there's one rider waiting, that is lambda 1. Okay, so that's the only change. Right, before I have one variable, now I have two variables. Questions?
But you're,
Yeah.
isn't the lambda now like stochastic or like you because you're faced with uncertainty about your price point, right? So
Exactly. So the uncertainty is at the 0, 1. So I don't know where I'm at when I arrive. I can arrive at 0 state, which just means I'm the first rider. I don't know whether I'm going to match or not. In this case, I'm going to be coded price lambda 0. If I happen to arrive, so the stochasticity comes in whether I'm in 0 and 1. So if I arrive at 0, I will see a price which corresponds to lambda 0. If I arrive at 1, means that if
Yeah, I guess I see what you're saying, but then don't they observe both prices if they're in zero? Because in the example that you showed.
Yes. Sorry about this. That's a very good observation. So here, this lambda zero, thinking about this lambda zero as the expectation of, sorry.
Yes. Oh.
Thinking about this lambda zero as the expectation of, I put it here.
Okay.
So
Okay.
there is some probability you're gonna pay this p prime zero. There's some probability you're gonna pay the p1. So thinking about this lambda zero as the,
Yeah. Okay.
if I'm the first letter, I'm gonna take expectation. Yeah. That's a good one. Sorry. So you can actually equivalently model this with this two-state Markov chain, just by doing this trick, that thinking about lambda zero as the expectation. So so this is what I say. So you can, using this lambda zero, suppose you have a solution of lambda zero and lambda one, you can always recover the first price by using this formula. This is basically how to equivalent, how to make the two system equal, I was saying. Okay, let's talk about the optimization problem, right? So now it's the same thing, right? Before it's just a single lambda. Now the only difference is now I need to optimize in two variables, lambda zero and lambda one, and then I still have this shared profit, right? And then there's some cases I'm going to get the shared profit, which is the price minus the cost, right? But here I'm actually summing up the two revenues in the column, right? So I have the first rider and the second riders. And in the second case, I only have solo. So that's the only difference. Okay. Surprisingly, you would think that now I have two decision variable, it will be a harder problem. Surprisingly, this is actually a much easier problem compared to a single variable problem. So before, I'm not sure if I mentioned this to you, that in the previous problem, which you had optimizing for the single static price, you actually don't have closed form solution. You have to solve a cubic equation. Here, you actually have closed form solution. So this, although I'm going to optimize in two, I'm going to come up with a price menu. This becomes an easier problem. Okay, so you gain tractability, and the reason for that is you really decouple the uncertainty. Right? Before, the difficulty is you have to think about the expected cost and then come up with the price. Now you price based on the outcome. You decouple the uncertainty. Somehow this gives you tractability. So you actually have, you have actually a closed form solution in this case. Okay, so let me talk about what's the additional benefits. Okay, so the additional benefits is, if you think about the optimal static price, let's go back to the previous proposal. Suppose you know the model, you're going to optimizing for the single static price. Sometimes the price curve can be weird. So the profit curve can look like something like this, right? So this is the optimal price point. And the reason why there's a kink at the beginning is because there's a phase transition. So if I price my, if price is actually too high, which means that there's low demand, so my cost is actually high. So I'm not gonna make money because cost is high, but if I start to decrease price, I become actually more and more efficient. So this entering into this phase transition where my profit curve can go down and go back up again because my price is so low so that there's more demand coming in so that the product becomes more cost efficient. So basically there's this tension of this phase transition here. This is the phase one where my cost efficiency is low. This phase two, which is my cost efficiency, is actually high, right? So what's going to happen with this static price is sometimes, let's think about this case. This case where my optimal price is actually somewhere here, right? But if I keep changing my model parameters, it will immediately jump to zero. So there's some kind of weird discontinuity in terms of this static price that as I change my market condition in terms of the demand rates, it can jump from some reasonable price point to something very, very high. Okay, so there's this weird, very weird discontinuity in terms of the static price. So that's one drawback. So it can show that with max-based price, everything's continuous. There's no this kind of weird jump in terms of price point. And also, it's going to always give higher profit to the platform because just thinking about the reduction, right? Before I have one lambda, now I have two lambda. So the optimal solution of this one lambda will always be a feasible solution of this two lambda. So intuitively, you will always have higher profit if you're using this two price menu. What's interesting about this is that if you think about this two price point, right? So if I'm the first rider, I see one price point. The second rider, I see another price point. You would think that the static price will be somewhere in the middle. What's interesting is that you can actually show when cost is high, both price can be low. Okay, so even if I arrive at the zero state in expectation, I'm actually going to have a lower price. So in a sense that you will have a price menu basically dominates the static price, because in expectation, no matter when you arrive in a system, either there's people waiting or not people waiting, you will always in expectation see lower prices. Okay, so this is a very good news for riders, especially when the cost is high and the demand is low. In the suburban area, when you're not able to match with people, this price menu, this two-tier pricing dominates the static price because both of the price point can be lower than the static price. Okay, and the intuition for that is because you de-risk the platform, right? The platform now is so willing to lower the price when there is matchable outcome. So in expectation, even for the rider who arrive with nobody waiting, they're actually paying low. So this is actually a very nice property. You can also show that it's always the case that the second price, the rider who arrived with somebody waiting will always pay low. So this is intuitive, right? So because I already have certainty about the match. Yeah, so if you look at averaging over all the riders, no matter where they arrive in 0, 1, have the same insights. Okay, so the intuition I already talked about, why this pricing policy can lower prices, because it de-risks the platform. The platform does not have to hedge against the risk of whether the rider is actually be able to match with somebody. It can use the matching outcome to calculate the prices. Okay. Another thing which is very nice is you can always show that if you look at all the riders, the amount the rider pays, right? Looking at all the riders that decided to convert, on average, they actually pay lower. And also there's lower cost per request, right? And a higher match rate. So the efficiency of you always improve the matching outcome. You have more people matches. And then you basically, this is saying that you always reduce vehicle miles under this pricing policy, right? Because you improve the amount of overlap. So the vehicle mile is also good. So there's good societal outcome of this. So the takeaway is that it's a win-win outcome. Both for the riders, you have lower prices, lower payment, you have higher match rate. For platform, you have higher profit, and for the society, you have lower vehicle mile travel. Good. So let's talk about so all these results I talk about is single origin destination. Let's talk about what happens with multiple origin destination, where you have people going from all kinds of origin to different destination. This becomes a much more complicated problem because you have this network effect, right? One origin destination is going to impact the efficiency of the other. So you can actually model this as a Markov decision process where the state is the amount of riders waiting with different origin destination types, right? Let me see if I have enough time. I don't want to. I have 10 minutes left. Yeah. Okay. Let me actually quickly jump through this. So these technical results are not that important here, because eventually what we're doing is we're trying to solve this large dynamic program, because you essentially have to figure out a pricing policy and a matching policy, right? So the state is the number of riders waiting with different origin destinations, thinking about what price you charge, who to match. And you can solve this dynamic program. And let me just jump directly to the result. Okay, so we did some very, we used the actual real rideshare data in Chicago. And the way we do this is we split the data. We have 8 weeks of data. We split into training and testing. We use the training data, the first 7 weeks, to estimate the rates, the arrival rates, and then solve for optimal pricing policy and matching policy. And then we run this in the testing. We hold up 1 week of data and then compare the outcome. Okay. And then what we're going to do is we look at different patients level. On average, people like to wait half a minute, 1 minute, 3 minutes, 5 minutes, and the cost per mile. So these are the driver cost. We look at, more costly situation, more, if people have more patients, then there's more matchability. And we compare two pricing policy. One is compute the optimal static price. So using some model to compute the optimal single price and also compare to the optimal two-tier price. Okay, so this is the outcome. Let me show you. So the first thing is that we do confirm that iterative pricing does overprice. So this is what we, using the Chicago data, I'm aggregating all the optimal price point originating from each census tract. So you can see that if I compare to the optimal static price, my iterative procedures always give me something higher. So this is probably not a good idea of using this iterative procedure in practice because it tends to price too high compared to what it should be. So we confirm this in the multiple origin destination. And if you look at the benefits in terms of profit and match rate, right? So we do have a lot of improvement in terms of profit, especially under the scenario where it's hard to match, right? So the patience is low and then there's not a lot of matchable demand. So especially the punchline here is that this two-tier pricing policy is especially effective in outskirt areas, thinking about suburban areas. And if you look at the payments, right? So if you only look at the, so there are two differences. On the left, I'm showing you the average coded price. So these are averaging over all the prices writers see. So the second plot is averaging over all the prices writer actually pay. Okay. So what happens is that with this new price, this two-tier pricing policy, people tend to see price slightly higher in the downtown area. So in a dense area, actually, on average, people see the price is going to be slightly higher compared to the static pricing. But there's a lot of improvement in terms of outskirt areas. So if you look at suburban area, we increased the accessibility of this product. And if you look at payment, right? So this confirmed with our select result. If you look at actually the prices average over all the out-of-pocket payment, it's always improvement. People always pay fewer compared to the static pricing. But there is a increase in the price people see in the downtown area. Okay. So if you look at cost efficiency, look at basically vehicle mile travel, right? So this is a case where you have zero cost efficiency because they cannot be put together versus a case you have 0.5 of cost efficiency because they can perfectly overlap. You can see that it's a tremendous improvement compared to static pricing. So the more darker blue means that you reduce the vehicle mile travel. Okay. So these are all very encouraging, confirming kind of our conclusion. So what's the point of this, right? So the idea is very simple. So what I'm trying to argue is that because of the uncertainty about who you're going to match to, static pricing or the upfront pricing people like about is actually not a good idea, right? Because you have to, because of the uncertainty, you tend to price higher. You want to factor into the uncertainty about whether you're going to match or not. But with this match-based pricing, it de-risks the platform. Produce a win-win outcome, have a higher profit for the platform, and also reduce price on riders and improve reducing vehicle mile travel. Okay, so this is the portion. I want to quickly jump to something I did kind of related to this is what I did actually this semester is actually I turned this thing into a game. Which is a pricing and matching game on ride sharing. So I actually asked my students, so the game name is Caliber. So I asked my students to form teams and I give them this data set. Let me just walk you through this. So I basically asked the team to come up with their own pricing and matching policy. And I'm going to measure them. I give them a data set and then I'm going to measure their performance in terms of the profit. Actually, let me just go directly to the thing I'm going to talk about. So I asked them to come up with a pricing function and a matching function, and then they're going to form a team. And then I'm going to compare their profit and vehicle mile traveled and rank them. And then that will basically, it's almost like a machine learning context. We have a set of training data, there's a validation run, and then they use the training data to develop the policy, and then we kind of compare them, right? So it's actually a very rewarding experience. Students really like it. we did this with GitHub Classroom, and it was actually we launched this in my graduate level supply chain class. This is what would actually happen. So if you look at this benchmark policy, right? So that's a policy I actually kind of investigated a bit. It's not the same policy in the paper, but some policy related to the policy in the paper. But there are in fact 3 teams actually beating my policy, so which is actually pretty impressive. But it's a good thing. So what we're doing right now is we're trying to improve this game through the summer, and then we might able to do another one with the T-Prep program at Cal, which is focusing on the transfer students. So we're actively developing this game, and hopefully we can have a public releasable version. If any educators are interested in using their game, just feel free to contact me. But that's another thing kind of related to this research I've been doing. Yeah, I guess with that, I'm just going to conclude. Let me just go back to the last slides. Yeah, I guess I will stop here.
Thank you.
Yeah.
Okay, and as per usual, first question from us students. We have a couple throughout. Trisha?
Yes, yeah.
That was a really great presentation. Thank you for presenting.
No, thank you.
So like the idea of shared rides is not new to some parts of the world. Like in India, there are these things called shared autos, and they've been around for a long time. And I think one thing that makes them very successful is density, like housing density. So I was wondering, like, you ever consider the aspects of housing density in these models, or let's say how a mixed use scenario is, so that you can get more trips and so that you can reduce this rate of arrival of greater passengers.
So the whole point, actually, the reason I started this project not focusing on the routing aspect, optimizing the vehicle routings, but instead of focusing on the pricing side, is actually what you were talking about, this density. So I do feel that increasing adoption and density, just because there's this phase transition, right? So it might not look appealing at the beginning, but if you have enough people who are doing this, then eventually you can break even. So I think the whole point of this is just trying to focus on improving density. And then if I would say the most efficient way of improving density within this framework is when you arrive, there is matchable request, you actually see a discount, right? So this is a very effective way of luring people to use share rides because the platform have information of these are already matchable requests. And there's this very cool idea about even converting people who actually request solo, right? So for example, if I want to request solo, I want to go from A to B without being interrupted. But there are actually certain share rides that you can actually do that, because thinking about you can embed this solo rides into another ride so that you're the last one to pick up and the first one to drop off, right? So in this case, you effectively are solo rides, but you just share with somebody. So what I'm trying to say is the platform, the whole punchline of this work is the platform has a lot of information about matchable state, right? Surfacing this matchable state to the demand by incentivizing them with these pricing mechanism is very, very effective. So actually, that's why I think my personal take is very similar to your judgment. So I think that the key to make people use is actually increasing density. Once you have enough density, you get to the place the price can be low, and then it's going to be sustainable. Yeah. Yeah.
It jumps from what Tricia said. Yeah, it's got the positive effect. So 2 questions. How much of the demand did you see, even in the games, go from solo to shared? Because in our heads would be like with less cars, less BMT. And the second would be how NGO have. If this model could be used instead of maximizing profit, maximizing access.
Yeah, so okay, let me go to the game actually. If you look at what the student did, Yeah. Let me just go to the result. Sorry. Yeah. So if you look at okay, the first column is the profit. The second column and then the third column, I guess it's related to your comment. That is the match rate, which is how many requests are matched. And then if you look at a top performing team, which is actually very interesting, it's a Pareto improvement. It has, compared to my policy, which is benchmark, it has higher profit, match people more, and then also reducing vehicle mile more significant. So it actually was winning the game with a lot of social benefits. So in this game, we don't have this we don't model actually how people, we don't model, so this is, everybody is using the share rights. So the only uncertainty is that sometimes they might not be able to match with somebody. But it will be interesting actually to modify the game, or even in a revision of the paper, we have to do that anyway, which is what we're currently working on, is looking at an extension of the model where you have the solo products and you have the shared product at the same time, and thinking about the pricing strategy of these two products, how they cannibalize with each other. Some early evidence we see is that this insight is robust. So even if you have an existing solo product, it's still better off to do the match-based pricing for your share rights product. So that's the early evidence we have. But the model will be a little bit different, but the intention is still the same. So your second question is about the objective.
Maximizing.
Yeah. So you could change the objective if you really wanted to be altruistic. You can change the objective just to be, for example, you can do maximizing. You can minimizing vehicle miles traveled, subject to you have to match, a lot of people. Let's say you have to have a target of. You have to match at least this amount of people, and then minimizing the vehicle mile travel. You can play these objectives. I think it can be explained in these terms. But even if you're thinking about profit, because it's kind of incentive is somewhat aligned, right? Because if you're able to reduce the vehicle mile travel, your cost is low. So even if maximizing profit, with this objective, we're already able to show that it has better vehicle mile travel compared to aesthetic pricing, even without using really kind of trying to minimizing vehicle mile travel. They already have these benefits because of cost is part of the profits.
Question online.
Yeah.
By
Would you
Maria.
mind reading it?
Yeah,
No, I can read it. No,
Okay,
I'm asking it by Carolina. How would you factor in safety perception of sharing with unknown people in a small space? Are there different models for men, women, and maybe low incomes?
Yeah, that's a very good point. So one thing we're actively working on is to explicitly model this inconvenience cost, right? So you have, if you answer, because one thing which is missing in the model is if you share with somebody, maybe there is a slight disutility about just having people in the same car. So we are working on that extension. As I said, it's still a similar tension that the model changed a little bit, but this insights of using this particular pricing strategy over a single price is still helpful. For the fairness of this, right? So actually, this is a very good question. One direction I've been trying to push is that this, I think, is related to the Chicago plots I'm showing you, right? So how this pricing strategy is going to increase accessibility of underserved community. Because what happens before is people just don't have access to cheap transportation options in this area because there's no match, right? So you have to ride solo. So one nice thing about this is maybe you can think, even like thinking about within this pricing strategy, are you able to shift the profit from certain region to the other, right? And then maybe with a little bit of reducing price, you can encourage even more demand, and then you can think about a more social planner's perspective. You can actually use the revenue from certain dense area to outskirt area, even if it's not profit maximizing, but it's maximizing social welfare. So there's definitely that part of our fund I'm very interested in too.
Thank you.
Yeah.
Joe, one thing you mentioned is that this sort of scaling problem that when you have a cheaper service, you attract more demand and then
Right.
you can get even cheaper, you grab a much
Right.
bigger market share.
Right.
So in your case, you pretty much have the demand sort of fixed, right? It's like a constant. Can you think maybe using like a non-homogeneous arrival rate and demand that
Yeah.
that incorporate this kind of positive feedback that
Yeah.
if you come up with a good matching and price strategy, your lambda is going to increase rather than.
Yeah, very good point. So I think this has a lot to do with like long-term effect of these things, right? Like because all I'm doing is very short-term. I think homogeneous, all the benefits here is trying to capture this in the same lambda, we saw the additional thing capture. But you're right, there's definitely long-term benefits of, if this product becomes more efficient, the lambda itself will increase, right? So that's the hope.
For Uber and Lyft, that's their goal, right? I mean,
Right.
They want
That's their
get a
goal.
bigger market, and also for society, you want to have a much higher lambda that
Right.
do sharing.
Right. So I think in some way, and this is just the way usually people try to capture that in practice, is trying to change the objective function instead of focusing on profit, which is more short-term, by adding kind of the welfare component, right? We can instead of maximizing the profit, but maximizing the total welfare you created. That definitely will reduce the price point a bit. It might not be budget balanced, but oftentimes this will induce long-term growth. So that's people have been thinking about is having this weighted average. Maybe there's a weights on the profit, and there's a weights trying to proxy of growth, right? Could be welfare, and it could be maybe super, even something like this. So, yeah, but you're right. So long-term effect is also sometimes it's also hard to measure because like these are basically churns, right? So you user, tech firm have a lot of way to measure churnings and so on and so forth. But my hope is exactly as that is if this can induce a long-term growth, and the land itself will even grow with this partition.
Yeah, the other thing about this ride sharing that also it really depends on the relative distance, the trip length
Right.
versus the waiting time, right? If you match me from here to San Francisco, I wait 10 minutes, it's not a big issue. But if I'm just come from here to Sacramento,
Right.
and then you let me wait 5-10 minutes, and that's like almost equal to my the travel time and
Right,
things,
right,
and
right,
then you
right.
can just go solo.
Right.
I was wondering when you consider your case, are you only matching the same origin destination? You're not matching different origin.
In analysis, all the direct analysis for origin destination, but the Chicago data is actually full scale.
Okay, so you can match different origins to the same going
Yeah.
to the same destination or
They
even
can-
different
They can
destinations.
even have non-trip overlap, right? You can have
Okay.
like, I'm not sure if that applies here, but you can have all the origin destinations are different, so you have to figure out what's the optimal drop-off sequence.
Okay.
Yeah, but you're right. So I think that would be even better because if you have longer trip, yeah, I think in the current setup, in the computation approach, not the analysis, I can definitely incorporate type-specific related weights. So that's fine to do, but for the Sirac analysis, yeah, because we assume it's the same origin destination, so it's the same. But yeah, that's a benefit.
Okay, yeah, one more time, let's thank our.